Hello everybody. Here is a screencast talking about the normal force, the tension force, some practice drawing free body diagrams, and also to introduce Newton's third law a little bit. So I'd like to consider that we have a squirrel at rest on a platform, and I'm sort of holding the platform with my hands. And so why is it that the squirrel doesn't fall right through the platform? Well, the platform has some chemical bonds in it that the squirrel would have to sort of crush and crack through in order to sort of shatter the platform and accelerate down through it. And I guess a given of the problem is that that's not happening. Another feature of matter is that it's sort of coated with shells of electrons, right? You learn this in chemistry. And so the shells of electrons on the outside of the squirrel are sort of pressed into the shells of electrons on the outside of the platform there. And so those electrons repel each other. And in fact, the more you push them together, the closer they get, and the stronger they'll push back in repulsion, because the repulsive force depends on how close together the electrons are. So that's why the squirrel doesn't fall through. You might pause the video and take a minute to draw a free body diagram of the squirrel. What does a free body diagram of the squirrel look like? Well, it looks like that. There's a gravitational force down on the squirrel. There's a normal force up on the squirrel. There's a dot to represent the mass of the squirrel. And that's that. How did I know to draw the up arrow the same length as the down arrow? That's what I attempted to do. How do I know that the normal force is equal to the gravitational force? Well, it's Newton's first law, which, remember, Newton's first law says that if an object isn't accelerating, the forces on it must balance. There must be no net force. An object at constant velocity, including rest, has a set of forces on it that are balanced. So I would say Newton's first law is the way that I can directly know that because there's no acceleration, that up arrow for the normal force has to be the down arrow for the gravitational force. So I've just used the word normal force to describe this sort of support force that the platform exerts on the squirrel, and indeed that is a type of force that we're going to encounter more of. So the value of the normal force in terms of the given mass of the squirrel is mass of the squirrel times gravity, because that right-hand side is equal to the gravitational force on the squirrel by our gravitational force law. What if I shift the situation such that the squirrel on the platform, that the platform is moving up and that the squirrel on top of the platform is being moved up all at constant velocity? Now can we draw a free body diagram of the squirrel and say how much the normal force is? I might pause the video. Well, again, this object is not accelerating. It has a velocity upward, but it does not have an acceleration because it's given that the velocity is constant. Because there's no acceleration of the squirrel, I know that the forces on it must balance, and the upward force must balance the downward force. The normal force must equal in magnitude the gravitational force, again by Newton's first law. There's a very strong temptation to say, it's moving up, so the up force must be stronger than the downward force. But that's not true because the squirrel is not accelerating up. So again, the value of the normal force is equal to the mass of the squirrel times g, the local gravitational constant. Well, what if I move the squirrel down on the platform with constant velocity? You've probably guessed that this will be the same: constant velocity, zero acceleration, balanced forces. So the normal force up on the squirrel is the same as the gravitational force down on the squirrel. Well, is it possible to have a situation where the normal force is greater than the mass of the squirrel times g? Is it possible for the normal force to exceed the gravitational force? Yes, that is possible. If that happens, according to this free body diagram, you can see the upward forces are stronger than the downward forces, so we have an upward acceleration. There's a net force up, which gives rise to an acceleration up. So what does an acceleration up look like? Does it look like motion up? Well, it can. Check it out. A velocity, I guess I'm sort of tacitly defining up as the positive direction here. An upward velocity that becomes faster and faster and faster. But keep in mind that a negative velocity whose magnitude is decreasing is also an upward acceleration. Both of these have upward accelerations. Here, it's possible for the squirrel to be actually moving downwards, but with decreasing speed. So either of these situations could correspond to a situation where the normal force on the squirrel outweighs the gravitational force. What happens if the gravitational force is greater than the normal force? Well, then there's a net downward force and a downward acceleration as a result. Does that mean that the motion has to be downward? Well, no. It could either be an upward motion with decreasing speed or a downward motion with increasing speed. What direction does the normal force always point? Is it always up? It's not always up. Nope. See here? The normal force is up when the platform is oriented up, but when I tilt the platform, you can verify, and we'll talk about later, how the normal force is actually at a right angle to the platform. So what direction does the normal force point? Perpendicular to the surface that exerts the normal force. In fact, the word normal means perpendicular. You'll probably learn more about that in your math class later if you haven't already. But when two vectors are normal to each other, they're perpendicular. And so we call this support force the force that describes the electrons of the squirrel refusing to be shoved through the matter of the platform. That force, the normal force, is called the normal force because it's always perpendicular to the surface exerting it. So, a normal force is a support force. It is one example of what we'll call a reactive force. If you remember that with gravity, we said, oh yeah, the gravitational force exerted on a mass m has a magnitude mg. We had a force law for gravity. I don't have a force law for you for the normal force because the strength of that platform exerting a force on the squirrel depends in large part on how hard circumstances are pressing the electrons of the squirrel into the electrons of the platform. In other words, it's the external circumstances of the situation that govern the strength of the force. There's no force law that I can write in equation form for you. I can ask you to solve for the normal force if I give you enough other information. But it is certainly not the case that the normal force always equals the gravitational force. That would only occur when you had a situation where there was a normal force up that precisely balanced a gravitational force, or maybe some other circumstances too. But you certainly can't say the normal force is just equal to mg. And the normal force is always directed in what direction? Normal to the surface. Here's another example of a force. It's a tension force. So if you could imagine me holding a string that sort of dangled a toy elephant below, then the toy elephant would have a tension force exerted upward by the string on it. Anytime there's a rope or a string that's pulling on something, basically if you look at this person sort of being pulled apart to the left and right by ropes, those ropes are exerting a force on him. And why is that? It's because the bonded molecules of the ropes within the ropes are refusing to be stretched. Okay, so if I'm holding a string and on the other side of the string is a toy elephant, then I guess I might ask, calculate the tension force in the string if that toy elephant weighs 2 kilograms. Well, let's start by drawing a free body diagram. The mass of the elephant has a tension force up and a gravitational force down. The tension force balances the gravitational force by Newton's first law and the fact that it's at rest. So the tension force is equal to the mass of the elephant times g, which is 2 newtons. Because g is about 10, is about a numerical value of 0.2 kilograms times 10 meters per second squared is 2 newtons. Great. Let's say that the elephant moves up with constant velocity, being pulled by that string. Well, as you can see, we're walking through the same sort of thought process as we did with the normal force and the squirrel on the platform. It's the same tension force when the string is being lifted with constant velocity, when the elephant is being lifted with constant velocity, as when it is just being held at rest. That is surprising because there is something upward about it, about the motion of the situation here. So you really do tend to want to be like, well, if the elephant is moving upwards, then there must be a bigger upward force than downward force. But forces give rise to accelerations, not velocities directly. So it's the presence of an upward acceleration that requires a larger upward force, not the presence of an upward velocity. Let's say we're lowering the elephant on the end of the string down with constant velocity. Again, constant velocity, zero acceleration, forces balance. So is the tension force always equal to the gravitational force? No. If I accelerate the elephant up or down by lifting on the end of the string and the string is tied, the other end of the string is tied to the elephant, then that's a situation where if there's an acceleration, there's a net force, and it sounds like in that situation the tension probably is not balancing the gravitational force. What direction does a tension force always point? It always points inward towards the string. So if I'm holding an elephant here and there's a string above it and the string is exerting a force on the elephant, that force will be exerted along the length of the string. The tension force is another example of a reactive force in that I can't give you an equation that describes the strength of a tension force. The strength of a tension force, if you imagine me pulling on a rope, the rope will be pulling on me in a way that depends how hard I'm pulling on it, because if you imagine that I'm separating the molecules within the rope, if I separate them a little bit more, they pull back a little bit stronger, trying to keep the string inextensible. Obviously, this is all assuming that the string does not break. Okay. The next thing that I'd like to talk about is Newton's third law, and there will be some demos that we'll do in class associated with that. But here's Newton's third law. If object B exerts a force on object A, then object B exerts a force on object A. If object A exerts a force on object B B exerts a force on object A, and the force of A on B is not considered the same force as object B on A. They're considered two different forces, sort of Newton's third law force pair. When object A exerts a force on object B, and object B exerts a different force on object A, those two forces are the same type, that is to say they're either both gravitational or both tension forces. They have the same magnitude as each other, but they point in opposite directions. You may have heard, like, every action has an equal and opposite reaction. I don't really know what an action is in the context of physics class. I'm not comfortable saying when there's an action, there's a reaction, because what is an action? I mean, it's not. I just don't know how to use that term precisely. Action and reaction also suggest that one comes after and one comes before, right? Like there's an action and then later there's a reaction. And this is not the nature of Newton's third law. When object A exerts a force on object B, at every instant, B also exerts a force on A. There's no lag. Why is Newton's third law true in the first place? This is actually a very deep question that if you ask physics teachers, they get a little sweaty. But the real answer is because a force of A on B is really like an interaction between those two objects, and it is the same interaction for both of them. So you don't need to fully digest that. You may be able actually to do a better job explaining why Newton's third law should hold. Maybe the most mysterious of Newton's laws. Newton's second law makes sense because heavy objects are hard to accelerate, or massive objects are hard to accelerate. But Newton's third law is tricky. Let's practice. A block rests on a table. See, there it is. There's a cartoon. Let's draw a free body diagram of the block and of the table. So here's the mass of the block. It's at rest. So I guess there's a gravitational force down exerted by the Earth. There's a normal force up exerted by what object? The table. The table exerts that normal force upward on the block. Well, here's the table's free body diagram. Goodness gracious, what does that look like? There's a gravitational force on the table exerted by the Earth. There must be a normal force by the block pushing down on the table. That must be the case because of Newton's third law. See this arrow here? The table exerts an upward force on the block. Therefore, the block must exert a downward force on the table. And I've written out FNB on T to sort of clarify here in the subscript. It's the block on the table. So the downward force of gravity acts on the table. A downward normal force from the block acts on the table. But the table's not accelerating down, so there must be a normal force up exerted on it by what? I guess the ground that it's resting on. And I guess the sum of these two downward forces must have the same magnitude as the upward force from the ground. So which are the Newton's third law pairs here? The normal force up by the block on the table, the normal force up by the table on the block, and the normal force down by the block on the table. Newton's third law. The table exerts a force on the block, so the block must exert a force on the table. Okay. If I draw a free body diagram of this skydiver, and we'll assume no air resistance, well, I guess just a gravitational force by the Earth on the skydiver acts down. Really? I mean, shouldn't we also have an up arrow? Because doesn't Newton's third law say that for every downward force there must be an upward force? Well, Newton's third law does say that. Let's finish the Newton's third law statement together. There's a gravitational force down by the Earth on the skydiver. So there's a gravitational force up by the skydiver on the Earth. And that is true. The skydiver exerts a gravitational force up. The skydiver has mass, so it attracts the mass of the Earth. The gravitational force by the skydiver on the Earth points upward. There are probably other forces acting on the Earth too, but I've ignored them here. And this force by the skydiver on the Earth is the same magnitude as this force by the Earth on the skydiver. In other words, the mass of the skydiver times g. So if there's an upward force on the Earth, why doesn't Earth fall up to meet the skydiver? It does. The Earth does rise to meet the skydiver with an acceleration equal to the mass of the skydiver times g divided by the mass of the Earth. But check it out, the mass of the Earth is so huge that that denominator is gargantuan, and the acceleration of the Earth upward to meet the skydiver is very tiny. One last idea on Newton's third law, or a drill, if you will. Let's say that there are two people in rolling chairs, green and red, and I'm going to ask you a series of questions, and I'd like you to think about, do you think that the force by green on red is more, or the force by red on green is more? Or are they the same, or is there not enough information? Well, in the first case, let's imagine that green and red have the same mass, initially zero velocity, they push off together with the same force. Well, I guess I've kind of given it away, huh? The force of green on red equals the force of red on green. But how about if red keeps his or her arms down and only green is doing the pushing? Does green exert more force on red, or does red exert more force on green? What if green is backed up against a wall and can't accelerate backwards, and only green pushes? Does green exert more force on red, or does red exert more force on green? What if green is huge, and is much larger, but both push? Does green exert more force on red, or does red exert more force on green? what if they have the same mass, but green is going to crash into red, and red's initially at rest? And neither of them physically push their arms. Does green exert more force on red, or does red exert more force on green? Well, all of these questions are Newton's third law questions. Newton's third law says, at every instant when green exerts a force on red, red exerts a force on green of the same magnitude and in the opposite direction. So the answer is C, the same force in every one of these cases. This is surprising because, we as animals with visual cortices tend to think, oh, the bigger animal is stronger, so it must be associated with more force. Or the more active moving object must have more zazz associated with it, so it must be exerting more force. Or here, green is constrained to not move, so red must be exerting, so it must be exerting more force on red, or something like that. No, same force by green on red as red on green in every case. Very good.